mapping between the analog cutoff frequency omega and the digital cutoff frequency omega in bilinear transformation. So this is a curve between the analog cutoff frequency and digital cutoff frequency. So digital cutoff frequency omega is equal to 2 tan inverse of analog cutoff frequency omega into t divided by 2. Now, now we are going to see a concept. We are going to see a concept called frequency warping. So in bilinear transformation, the relation between analog and digital frequencies is non-linear. So it is not, from this graph we understand that it is not linear and the relation is non-linear. So when the S-plane is mapped into the Z-plane using bilinear transformation, this non-linear relationship introduces distortion in the frequency axis, and which is called frequency warping. So what is frequency warping? In bilinear transformation, the relation between the analog and digital frequency is non-linear, and when the S-plane is mapped into the Z-plane using bilinear transformation, this non-linear relationship introduces distortion in frequency axis, which is called frequency warping. So in order to prevent this frequency warping, we are going for pre-warping. So in IAR digital design, filter design using bilinear transformation, the conversion of the specified digital frequencies to analog frequencies is called pre-warping. The pre-warping is necessary to eliminate the effect of warping on amplitude response. So now we are going to see the effect of warping on magnitude response by considering a diagram. So this is nothing but the magnitude response. So this is the analog cutoff frequency omega, and this is a digital cutoff frequency omega. So at low frequency, when you are converting from analog cutoff frequency to digital cutoff frequency, the frequency is expanded. What is happening? The frequency is expanded. And at a high frequency, when you are converting from analog frequency to digital frequency, the frequency is compressed. So here the frequency distortion is occurring. So this phenomenon is nothing called frequency warping. What is frequency warping? Due to, while converting from analog cutoff frequency to digital cutoff frequency, at low frequency the frequency is expanded, and at high frequency the frequency is compressed. So this distortion is occurring, and this distortion is nothing called frequency warping. So similarly here, so this is your phase response, this is magnitude response, this is phase response. So while converting from analog cutoff frequency to digital cutoff frequency, here also the curve is not same as in the analog. So it is changing. So here also distortion is occurring. So these are occurring due to the frequency warping. So the warping effect can be eliminated by pre-warping the analog filter. So in this method, the specified digital frequencies are converted to analog equivalent using the equation sigma is equal to, omega, the digital analog cutoff frequency omega is equal to 2 by t tan omega by 2. This omega is something with the digital cutoff frequency. And here you are having two expression, that is omega p is equal to 2 by t tan omega p by 2, and omega s is equal to 2 by t tan omega s by 2. This is for pass band and this is for stop band. P is for pass band and S is for stop band. And these frequencies are called pre-warp frequency. Using the pre-warp frequency, analog filter transfer function is designed, and then it is transformed into digital filter transfer function. So now we are going to see the steps to design a digital filter using bilinear transformation technique. So what are the steps needed to design a digital filter using bilinear transformation technique? The first step is from the given specification. They will be giving the specification. From the specification, first find the pre-warping analog frequencies using the formula analog cutoff frequency omega is equal to 2 by t tan omega by 2. This omega is nothing but the digital cutoff frequency. Using the analog frequencies, find h of s of the analog filter. Select the sampling rate of the digital filter. Call it t seconds per sample. Then substitute s is equal to 2 by t 1 minus z inverse divided by 1 plus z inverse into the transfer function found in step 2.